Hello, calculus students and seekers of truth. Welcome to the continuing series of videos on improper integrals. And in this video, we will deal with integrals that have discontinuities. And these are not just any discontinuities, they're discontinuities towards infinity or negative infinity. So this integral, this definite integral here may seem like a simple one, and I will give you the most common wrong solution that you will ever see. The integral from 0 to pi of secant squared of x dx. The antiderivative of secant squared is tangent, evaluated between 0 and pi. Tangent of 0 is 0. Tangent of pi is also 0. This is tangent of pi minus tangent of 0. And if you did it this way, you would say, well, that's what the whole thing equals 0, but you would be so very wrong. Okay? And the reason for that is let's take a look at the graph of secant squared, and it looks like this. Okay? This is the graph of secant squared from 0 to pi. Okay, so here's at 0, here's at pi. So what we're trying to calculate is these two areas here. Now, you can clearly see that this is not equal to 0, and you can see the pitfall of assuming that it is, and this just works because, again, secant squared has a discontinuity here, and not only is it discontinuous, these curves approach infinity. Now, these little areas in here between the vertical asymptote and the curve, it gets smaller and smaller and smaller and smaller. And so the question is, does that really, narrow down to anything as we get closer and closer to pi over 2, or does it diverge? Okay? So whenever you have an integrand that has a discontinuity, you have to split it into two different integrals. So we're going to integrate from 0 to pi over 2, and then from pi over 2 to pi. So the integral of secant squared from 0 to pi over 2 plus the integral from pi over 2 to pi of secant squared dx. Okay? And we know that weird things happen at pi over 2, so we're going to have to use some limits to complete our integration. So the first integral here, we're going from 0 to pi over 2, but we can't ever actually reach pi over 2, so we're going to say from 0 to b and take the limit as b approaches pi over 2 from the left of secant squared dx plus the integral from pi over 2 to pi. No problem here at pi, but at pi over 2 the same thing happens. You can't ever start at pi over 2 because it's undefined there. So this is a, and this is going to be the limit as a approaches pi over 2 from the right. Of secant squared x dx. Okay, so the notation's a little bit messy, but at heart all we're really doing is computing this antiderivative and then a limit that goes along with that. So the limit as b approaches pi over 2 from the left of the tangent of x, because the antiderivative of secant squared is still tangent, from 0 to b plus the limit as a approaches pi over 2 from the right of tangent of x. Excuse me, I'm writing off the screen here. Of the tangent of x evaluated from a to pi. Okay. So now let's evaluate this. This is tangent of b minus tangent of 0, taking the limit as b approaches pi over 2 from the left, and then this is plus the limit as a approaches pi over 2, the tangent of pi minus the tangent of a. So I'll put square parentheses just so that you can see we're taking the limit of this whole entire expression. And this should be pi over 2 from the right. Okay, so tangent of 0 is in fact 0, so we don't need to worry about this. Tangent of pi is also pi, so we don't need to worry about, is also 0, so we don't need to worry about this. And now we just have to figure out what is the limit of tangent as you approach pi over 2 from the left. So let's think about this, and you can also look at a graph of tangent to ascertain our answer. Okay. So the graph of tangent, if you recall, is periodic, and it looks like this. And I have just sketched in the part that really matters, that we're really interested in. So first, let's look at, so you can see here, this has a bunch of vertical asymptotes. And as you approach pi over 2 from the left, this goes to positive infinity. And if you approach pi over 2 from the right, it goes towards negative infinity. So over here you have a negative infinity, because you have this negative in here. So you end up with infinity plus infinity, which is also infinity. And this notation here is not great. It's not really a good way to write out some arithmetic, but you can just say, you can just think of it this way: a very large number minus a negative very large number is the equivalent of adding two very large numbers, which will also equal another very, very large number. So that means that this integral does not exist, or at least it diverges. It just gets bigger and bigger and grows towards infinity.